Okay, I think we can officially start off now. So I'll just quickly go over this again. So yeah, the story started within University of Ghent, where the corona pandemic changed quite a lot for us. If I'm now able to go to the next slide, perfect. So yeah, as I told you before, the college was suspended. We weren't able to get a drink anymore. So that's actually when we started Jugend Racing. So an initiative where we were building a fully self-driving electrical race car. And after 2 years of really working very hard on the car, first completely remotely, after which, when the corona pandemic finally started going down, we were able to build this, in my opinion, quite beautiful car. So really during this time within Jugend Racing and really building the team and constructing this race car, there were actually two main aspects to us that really kicked off and really started showing to us. So the first one is by really working closely with other companies, we noticed that there is this enormous gap between the academical knowledge and the technological advancements within the university compared to the technological implementations that there are within the business units and the business as we know it today. So this is really one key aspect that we noticed, and that's something we really want to do something about. Another aspect that we really noticed was, it was kind of a pivotal moment for us, is actually during the last 2 years, sustainability has become an increasingly important aspect in our lives as well, really by the continuing disasters, both in increasing intensity, but also in increasing frequency. For example, here, the wildfires in San Francisco, which turned the sky completely orange, or the floods even here in Belgium are starting to happen more and more, or happen to be way more intensively as well. Another one, increasing more winds, more storms. And all of this is also really turning into social unrest. We are seeing protests around the globe. Even here in Belgium, we've seen quite a lot of them last years. So we really started wondering and thinking about how can we use the technology that we saw within Jugend Racing, within the university, how can we use that technology to have an impact on the sustainability aspect as well? Because we've seen what this technology can do. We know that technology is an enabler for sustainability. And more importantly, we also know that technology is able to solve these sustainability goals and really the ESG goals in general. So that's actually the moment when Polysense was officially founded. Together with our investors, Peter Hinzen and Alexander de Wolf, we started our journey and we started thinking about, okay, now we really want to implement those technologies within business processes, but also to have that impact on the sustainability goals. So we started looking at things that are happening now at the moment within the governments, within regulations, etc. And one thing that we clearly noticed was obviously the Green Deal. I think most of you will already know what the Green Deal is. But it really means that within 2050, we want to achieve net zero business processes within Europe. More importantly, the milestone Fit for 55, but is only within 7 years, so in 2030, where we want to enable 55% less carbon emissions within business processes as well. And we also noticed that this cannot happen without the implementation of technology. So here again, we started looking at the different scopes that this regulation starts putting forward. So the first scope is all about the direct emissions. So we'll be looking at emissions resulting from the business processes at the sites of the company itself. So it are really the fossil fuels that are burned by the companies by producing goods, offering services, driving with your own organizational cars, etc., etc. The second scope, scope 2, is more about the indirect emissions resulting from energy that you consume at your company. So this could be electricity or emissions resulting from electricity consumption. More importantly, this scope is really varying because you can use electricity resulting from green energy sources, but you can also use them from other more polluting sources as well. The third pillar, scope 3, is all about the other indirect emissions. And it's all about, for example, when you buy goods and you want to sell goods, you need to transport them from your production site to your customers, to your distribution centers. And these are all emissions that are accounted for in this third scope. So we took a step back and we thought like, okay, how can we use the technologies that we've seen and enable them in each of these scopes to make sure that we can reduce the emissions in those scopes as well. The first scope, we've noticed that quality control, resource and waste both the management and the optimization, but also the process optimization are really AI cases that is really efficient in this scope, mostly because we can increase efficiencies here, but also decreasing the emissions resulting from those production processes or business processes. In the second scope, we can look at energy management systems. So really thinking about how can we efficiently optimize our energy usage, but also how can we decrease the energy usage that we have today? And how can we think about smart grids that can more actively go looking for green energy instead of energy resulting from more polluting energy sources? Once that we have this in the second scope, we can start looking at the third scope, obviously. And this third scope is all about smart logistics, also supply chain optimizations, so that we can decrease all our emissions based from transportation of resources, productions, services even, to have an impact here as well. Now, this is all about the indirect impact of technology. It's important to also notice that this indirect impact, obviously, it's quite positively because we are able to reduce emissions from these technologies. But these technologies itself, they have a direct impact on the climate as well. Technology in general, they are using energy. They need to be produced when you're using computing chips, for example, CPUs, TPUs, GPUs. They need to be produced. Raw material need to be extracted. And this is all accounted for in their own emissions and their own impact on the climate. And this is a scope that most companies and even engineers in general are not thinking about at the moment. So you need to extract your raw materials. You need to produce your hardware. So as I said before, your GPU, TPU, CPUs. Then you have the usage of those algorithms itself. So you need to run your algorithms. You need to run your computational power. This has also a quite significant energy consumption itself. And then after you've received your goals and achieved your goals, you need to have an end-of-life disposal. So are you going to just dump your chips on a waste belt, or are you going to recycle them? Think about how can we optimize this and extract the really valuable materials in these chips to reuse them in other chips. So this is also quite important to think about when we're starting to develop technical solutions and, more importantly, AI or neural networks in general. Now, in the upcoming slides, I will mostly look at both the usage of the algorithm, because I think this is one of the most important factors that we can start optimizing in today. And quite frankly, now we also see a quite worrying trend, in my opinion, because nowadays we've seen a trend, especially with ChatGPT 3 and GPT-4, where we're just increasing on parameters. We're adding on parameters to increase the accuracy. We're still looking at increasing capabilities, increasing the performance of those algorithms as well, but without really thinking about how can we make those energy efficient algorithms. Because adding more parameters, it's all quite nice, but more parameters also means that you need more data to train those algorithms. More data means you need bigger data centers to train those algorithms. So already here we can see that, there is a worrying trend about the rising energy consumption that is needed to really achieve this better accuracy and this better performance. So what is our goal? Our goal is really to find and think about the perfect balance between both the direct and the indirect impact of those algorithms. So for example, here, we can see that we start with a certain carbon emission level. We will decrease it by the indirect impact of implementing those technologies. However, due to the really rising energy consumption of those algorithms, here we will leave with a net negative result because of the energy consumption of those technologies. And our goal really is just to lower the direct impact of those algorithms to make sure and to enable net positive results within those business processes. Now, as an alumni team captain of Jugend Racing, I often get the question, Jarne, when are we going to see fully self-driving and autonomous race cars or just cars in general? Unfortunately, I will not be covering that topic here today. But however, I think that autonomous cars and self-driving cars make a perfect example of how we can use or how we can demonstrate the impact of direct and indirect impacts on those technologies. So just a few weeks ago, that I've seen this study from supported by Volvo, which states that if you enable adaptive cruise control within your car, you can achieve a 5 to 7% drop in fuel consumption just by enabling this process. And this already started getting my hopes up, actually, because just wonder what you can achieve when you enable a full self-driving car. You can even achieve higher accuracies, higher efficiencies. So this would mean that you would have a higher drop in fuel consumption. However, shown by a study by Taraki, it is even showed that by enabling fully self-driving algorithms, that you have a decrease and even a 30% decrease of your range of your autonomous vehicles. And this means this is just resulting based on the energy consumption of all the AI models, neural networks that are based within this car. So here, I think it's already quite important to think about how can we optimize our algorithms not only to achieve higher efficiencies, but more importantly, to get a net positive result here as well. So to make it a bit more concrete, let's take a specific example. So let's just suppose that you're an engineer within, just going to put that off. Just suppose you're an engineer within one of those car manufacturers that want to enable a full self-driving car, and you're tasked with the responsibility to think about detecting the cars at the road, detecting the pedestrians on the road, detecting even the traffic lights on the road, and also to track them through different frames so that you know within each frame that a car from the previous frame is the same car in the frame that you are in now. So let's just take this stream as an example. If we start thinking about this, you need actually 4 main topics that you will need to consider. So first of all, you will need a camera. I think that's quite straightforward because otherwise you will not have an input stream on which you can process your data. But already in the choice of your camera, you can have a significant impact. Just going back to the slide from before, this camera will have raw material extraction. This camera will need to be produced. This camera will consume electricity from its own, etc., etc. So already here, by choosing a different kind of camera, you can have a lower net emission resulting from your application or your solution. The second one is the compute power. So you can think about using CPUs, GPUs, TPUs. They all have their own power consumption, their own emissions resulting from producing these units. Then you need to train your algorithm. So you will need quite a lot of data. You will need quite a lot of computing power to train your algorithm. And after that, you will also need to run the inference. So really start using your algorithm. And also, obviously, this step increases energy consumption and will have an impact on the climate. So in the coming slides, I will start looking at the compute unit and the inference only. The camera and training are topics that I will not cover today, but it's certainly interesting to think about those as well. So let's just assume for the first one that I use an Intel E7 CPU to start processing the stream and to start running object detection algorithms, or more importantly, AI algorithms. The model that I used, maybe also important to note, is a YOLO V7 model for running the object detection, and a strong sort model to really start tracking the different objects through the frames. So let's just to monitor and to have an idea of the electricity consumption of your algorithm, I used CodeCarbon. So CodeCarbon is actually an open source tool that is able to monitor the electricity that is consumed by running the algorithm throughout the frame. So everyone is able to use CodeCarbon. So if you haven't used it before in your code or your solutions, I would highly recommend this tool to have already kind of a grasp of the electricity that you are consuming just by running this algorithm. So let's take a look at the result. The stream isn't really coming through, but here on the screen, you can see it quite nicely. So this algorithm is actually able to start detecting the cars, but also start tracking the cars through the frame. For example, the blue car here in front, it keeps getting the same ID, so 267. So it means that the algorithm is also able to know which car it is throughout the frames. We can see that the algorithm has some problems with cars in the background, but for now, we will do it with this one. So if you now look at the energy consumed by just running this algorithm, we can see that it's actually quite significant what kind of impact and what kind of emissions and electricity that we used throughout the usage. So we can see here that the title drops a bit off the screen, but that the CPU inefficiencies really result in high energy usage to run this algorithm. For example, if we take a Tesla Model 3, it consumes about 14.9 kilowatts hour per 100 kilometer drive. This would mean that by running this algorithm and just enabling this algorithm on a Tesla, that you would have lost 100 kilometer range after a 6-hour drive. So I think, in my opinion, this kind of shocked me, to be honest. These are numbers that are quite high and also quite significant in your range of your car. So we have with Polysense the privilege to be working with Mieke de Ketelaere. So Mieke de Ketelaere is actually the leading lady in AI, but she's also one of the first that started thinking about this and started to think about, okay, how can we build a framework in which we can see how we can start optimizing these solutions to lower this impact. So she came up with the M2T2 framework. And this framework actually consists of two main dimensions. So the first one is the hardware dimension. And within the hardware dimension, we will start looking at both the model and the type of the hardware, but also the time or the selection on which we run the solution. So the type of hardware, I think this one is quite straightforward. We can start using different chips. We can start using other compute units, for example. But also the time and the location will be quite important, especially for training those algorithms, because when you use servers to train your algorithms and you use a server, for example, that is stationed here in Europe, it will be more efficient to run your algorithm over day, because over day here in Europe, we have more availability of green energy sources, for example, solar. While if you train your algorithm in the United States on a server, it will be more efficient to train it at night, because at night temperature in the USA are quite low. So this means that your servers won't need that much cooling anymore at night. So already here we can also see that just by the time and the location of where you train your algorithm, you can achieve an impact on sustainability. Now, in the coming slides, I will look at the type of hardware that we can use. So this is a quote from Russell Klein. So he says that GPUs can perform an inference using a fraction of the energy that you would need with a CPU. So this might seem a bit controversial at first, because obviously GPUs need way more energy compared to CPUs. But it is shown that a GPU is able to have way more, it's just way more efficient in processing AI algorithms in general. And that's why it will also be less energy consuming. So let's take an example. Just on the same stream as before, we will look at the NVIDIA GeForce RTX 36 to run the same algorithm as before. And we will then look at the energy usage of that algorithm. So now we've only consumed this much amount of energy for the same 4-minute stream as before. So if you take the same example as before with the Tesla Model 3, this means that we can now drive for up to 86 hours before we will lose the same amount of 100-kilometer range. So already here we can see that we have achieved a factor 14 of more energy efficiency just by selecting a different type of hardware. So this is already quite, a nice result in my opinion, but we can take this way more further. So this is just by using a different compute unit, but the M2T2 framework also shows a second dimension, namely the software dimension. And on the software dimension, you have also different capabilities on which you can improve your efficiencies. For example, you can select different AI models. You can select different AI architectures on which you can run your models. Or you can change the method. So the method of processing. Are you going to prune your networks? Are you going to lower the amount of parameters within your neural network? All these things will have an impact on the energy efficiency of your model without affecting the accuracy of the model too much. Let's take another example. So once again, run on the NVIDIA GeForce RTX 3060. We will now use a different model. So still YOLO V7, but now we will take YOLO V7 Tiny as an example. So YOLO V7 Tiny is a way smaller model compared to the YOLO V7X from before. So if we look at the results here, we can see that the algorithm is still able to detect cars. However, we see that it has quite some difficulties with cars that are quite far away from the camera. And we can also see that, especially in the background, it starts doubting quite a lot. So it changes classes from between different frames as well. However, the tracking device is still working quite nicely, as we can see with the blue car, because the blue car is still getting the same ID throughout the different frames. Now, if we see this result, it's also important, again, to think about the energy consumption of this algorithm. And now we can see that compared to the previous two, that we have really achieved quite significant gains in the efficiency. So once again, taking the same example as before with the Tesla Model 3, we can now see that we can have a drive of more than 95 hours of driving before we will be losing the 100-kilometer range, which we talked about before. Compared to the previous one, this means that we've once again increased our energy efficiency with a factor of 4.4. So in total, compared to the very first experiment that we did, it's over 40 times more energy efficient to use this algorithm with this compute unit compared to the CPU or the bigger model that we used before. Now, the question that we really need to ask ourselves is, do we really need more accuracy? I told you before as well, with the increasing amount of parameters, most engineers, and especially data engineers, are looking to how can we increase accuracy of a model, and how can we do this by mostly of the time adding parameters, using bigger models, and really, upping the energy consumption of those models as well. But especially in this case, for example, this is a bigger model that I showed you before. It is able to detect the cars in the frame quite nicely. But here is the same frame with the YOLO V7 Tiny model. And we can see that it's also able to detect all the cars that are quite in front of the camera. However, the cars in the back one that are parked near the apartment, they aren't detected at all. So here we need really to ask our question, is accuracy a good metric in this use case? Can't we think of anything else that also takes into account the energy efficiency of the model? But also, do we need to detect the cars that are quite away in the frame? Isn't it enough to just detect the cars that are quite close by the camera? And will it not be sufficiently to enable fully self-driving capabilities? So I think this is really important that we start thinking about this now, because with this increasing trend of rising energy consumption within AI and within AI models in general, I think we're not really heading in the correct direction. So I really would like to point out that technology and innovation are really a key to enable this sustainable future, and we cannot think about a future without this technology. The second one is also that we really need to think about the energy consumption of those AI algorithms or AI projects, because if we don't start thinking about this energy efficiency now, I think we will be heading towards, not that of a negative, positive future, let's say. And then lastly, I want to say that we really can achieve a net positive business processes, and that we can do this, but we need to do this together. And more importantly, we need to do it now, I think. So to end this keynote, I would like to end with a quote from Stephen Hawking that is more applicable now than ever, I think. And that is that intelligence is really the ability to adapt to change. And I think the change, or the time to change, is really now. So thank you for listening.